morning all of you. Myself Archana Sharma from Noida Institute of Engineering and Technology, Pharmacy Institute, and I am here to deliver my lecture on the topic theories of emulsifying agent. So, when two immiscible liquids are agitated together so that one of the liquid is dispersed as small droplets in other. To prevent collisions between globules, it is necessary to use emulsifying agent. So, what happen when we prepare the emulsion? Okay. When we prepare the emulsion, there is a two phase. Okay. What we do? We dispersed the one phase into the other phase. Okay. Okay, into a small fine droplets, and to prevent these two globules of the dispersed phase from getting collide, okay, what we do? We add a emulsifying agent. So, in the previous lecture we have discussed about the nature of the emulsifying agent. Okay. So, emulsifying agent, what they do? They form a protective layer around the each globules of your dispersed phase, thereby prevent the tendency of collisions. Okay. So, based on the nature of the film formed at the interface, the mechanism of action of emulsifying agent is described. For example, first is monomolecular adsorption and film formation, second is your multimolecular adsorption, third is your solid particle adsorption. Okay. So, what will happen actually here? There will be a interface acting between the oil and water phase. Okay. So, at this oil and water phase junction, this emulsifying agent they act and they reduce this interfacial tension acting between the two different phases. Okay. So, depending upon their nature, what type of film is formed on the film is formed at the interface of the oil and water, the nature or the mechanism of emulsifying agent is described as monomolecular adsorption and or film formation, multimolecular adsorption, and third is your solid particle adsorption. So, first is your monomolecular film. Surfactant are substances containing both hydrophilic and hydrophobic regions. That is why they are amphiphiles in their amphiphiles in their molecular structure. These reduces interfacial tension by getting absorbed at the oil water interface in such a way that lipophilic non-polar groups are oriented towards oil, while the hydrophilic polar groups are oriented towards the water, thus forming a stable emulsion. So, as we all know that your emulsifying agents are having both hydrophilic and lipophilic part in their structure, okay, and they reduce the interfacial tension by getting absorbed at the oil and water interface. Okay. So, they orient themselves in such a way that the polar part of the surface active agent are aligned with the water molecule, and the non-polar part of the surfactant align themselves with the lipophilic or the oil phase of the emulsion. This film act as a mechanical barrier to collisions of the globules of the dispersed phase. So, the film which they formed it acts as a mechanical barriers, and they prevent the collisions of the globules of the dispersed phase. Thus, as interface, the two surfactants interact to form a complex and condensed film as a monomolecular film. Okay. So, at the interface what will happen, the two surfactant, that is the polar and the non-polar junction of the surfactant, they align themselves in such a way that they form a complex and a condensed monomolecular film at the interface. A good emulsifying agent reduces the surface free energy and hence the tendency of collision. So, as we all know that if we are going to increase the surface area, then the surface free energy of the system is also increase. Okay. So, in the emulsion what we do? We disperse the oil phase into the fine droplets, okay, into the fine droplets, clear. Thereby we are increasing the surface area of the oil phase and the overall surface free energy of the system. Okay. So, a good emulsifying agent, they reduce the surface free energy and also they prevent the tendency of the collision between the two globules of the dispersed phase, because the surface free energy is your G is equal to, that is lambda oil in water into delta A, where this is your interfacial tension between the oil and water and this is the change in your area, and it is necessary. So, because the surface free energy is G is equal to lambda oil in water into delta A, and it is necessary to retain a high surface area for the dispersed phase. Any reduction in interfacial tension will reduce the surface free energy and hence the tendency for collision. So, for making the system stabilized, it is necessary that the oil should be dispersed in the form of fine globules. Okay. So, we cannot reduce the surface area of the dispersed system. Okay. We cannot reduce the surface area of the dispersed phase, but any attempt, if we are going to reduce the interfacial tension, okay, if we are going to reduce the interfacial tension, and that will reduce the surface free energy of the system and hence they reduce the tendency of collision between the two globules of the dispersed phase. Okay. The fact that the dispersed phase droplets are surrounded by coherent monolayer, that helps to prevent collisions between two droplets as they approach each other. Ideally, such a film should be compact and strong, so it cannot be easily distributed or broken. So, we all know that when we are preparing the emulsion, we add a emulsifying agent. So, with in that emulsifying agent is going to surround the globules of the dispersed phase, and thereby they prevent the collision between the collision between the two globules of your dispersed phase. So, this is a layer, this is the protective covering of your emulsifying agent, which prevents the collision between the two globules of your dispersed phase, okay, whenever they approach to each other. Ideally such a film should be compact and strong, so that it cannot be easily distributed or broken. So, the film, this emulsifying agent will form at the for protecting the globules of the dispersed phase from getting collide. That film should be compact and strong, so that it cannot be easily distributed or broken. For any reason, if the film is broken, it should be elastic and flexible enough, so that it can reform rapidly on moderate agitation. So, in any case, in any circumstances, such as during transportation or any vigorous shaking, if the film is broken, it should be, the nature of the film should be so much elastic and flexible that they should reform immediately on giving a moderate agitation, thereby preventing the collision of the oil globules or the globules of the disperse phase. Attempts have been made to use a combination of surfactant rather than single one for better stability. So, for achieving such type of forming a such type of surfactant film, generally we use a combination of surfactants. It is assumed that they support each other and strengthen the monomolecular film. So, it is considered that the combination of the two surfactant forms a more compact and a strong monomolecular film at the junction of the oil and water phase. The surfactant blend consists of water soluble and oil soluble surfactant. So, the hydrophilic surfactant approaches the interface from aqueous phase side, while the oil soluble surfactant approaches from oil phase side. Okay, so, what we do? We take a blend of surfactant which contains suppose if we take a two surfactant such as A and B, then we prefer that one out of the two surfactant, one is more hydrophilic in nature, okay, and the other surfactant should be more lipophilic in nature. Okay. So, what will happen if if one surfactant is more hydrophilic in nature, then it will form a protective or it will approaches the interface from the aqueous phase side, while if the other surfactant which is more lipophilic in nature, it will approaches the interface from the oil phase side. At the interface, the two surfactant interact to form a complex complex and condenses as a monomolecular film. So, what will happen? Suppose this is a oil phase, this is your water, and in between there is a interface. This is your interface. So, at this interface, the two surfactant, okay, let us take A and B, they approaches in such a way that they interact with each other in such a way that they form a complex and condense as a single monomolecular film, that is they form a single layer of film and thereby protecting the globules and preventing the collisions. A combination, for example, in this a combination of sodium cetyl sulphate and cholesterol leads to a closed pack complex film at the interface that produces an excellent emulsion. So, if we look into this figure, here we take the two emulsion, that is sodium cetyl sulphate and cholesterol. So, combination of this two film form a strong condensed film and they protect the oil globule. Okay. However, it should be stressed that a blend of surfactant may also produce a poor quality emulsion if the interaction between them is not strong at the interface. However, it is also observed during the preparation of the emulsion that if we have chosen the two surfactant that is not compatible, okay, that also may produce a poor quality emulsion if the interaction between the two emulsion is not strong at the interface. So, for example, sodium cetyl sulphate and allyl alcohol, these are the two surfactants, okay, and they do not form a close packed film, therefore, their combination produces poor emulsion. So, if we are taking the sodium cetyl sulphate and allyl alcohol, so when we take the combination of these two surfactant, they do not the film which they formed at the interface, it is not condensed, it is not a closed pack film. So, their combination makes a poor or a unstable emulsion. Another example is your cetyl alcohol and sodium oleate produces a closed pack film, but complexation is negligible and therefore, again produces poor emulsion. The another example is cetyl alcohol and sodium oleate, they form a condensed condensed film at the interface, but their compatibility, the complexation between the two surfactant is negligible, and hence again they form a poor emulsion. So, if we look into this diagram, first one is the sodium cetyl sulfate and allyl alcohol. They are compatible, but they form a, they do not form closed packing, okay, in this case. Hence, the poor quality of emulsion will form, poor emulsion will form. Another example, that is cetyl alcohol and sodium oleate. Okay, in this they form a closed packing, okay, although they form a closed packing, but the complex between the two surfactant are not strong, is negligible. Hence, again in this they form a poor emulsion. Okay. So, the two surfactant which we choose for preparing the stable emulsion, that needs to be compatible with each other. So, surfactants are capable of reducing the interfacial tension. This facilitates the immediate formation of small droplets. Delta A is increased due to the formation of small globules. Usually these small globules tends to combine with each other and form separate phase. So, delta A cannot be altered to get delta G. So, as we all know that these surfactants, they are going to reduce the surface tension between the two different phases. Okay. Since there is an increase in the overall area of the system, because the dispersed phase is acting is present in a small globules, okay, and if we try to reduce the area, we can reduce the surface free energy of the system, but in practical sense we cannot reduce the area, because if the area is reduced, then what will happen? Okay, phase separation will take place. So, we cannot reduce the area. So, the only attempt is that we are going to reduce the interfacial tension, and that is what the objective of the surfactant agent. Okay. So, in this ionic surfactants imparts charge on interfacial film. These film exert repulsive forces between two approaching globules and prevent collision. This mechanism is of minor importance. Non-ionic surfactants also produces a good emulsion. In such a case, ions present in the aqueous phase often get adsorbed onto the monomolecular film, thereby preventing the collisions of the droplet. So, in case of non-ionic surfactants, if we choose a non-ionic surfactant, then in that case what will happen? The ions present in the aqueous phase, they adsorb at the monomolecular film, and thus they prevent the collision of the droplets. The type of emulsion that is produced, oil in water or water in oil, depends primarily on the property of the emulsifying agent. So, we have already discussed in the previous chapter that whatever the type of emulsion will form, that depends upon the nature of your emulsifying agent. Okay. This characteristic is referred to as HLB of an emulsifier, and this nature will be will be taken by the by knowing the HLB value of an emulsifying agent. The balance of hydrophilic and lipophilic properties of an emulsifier determines whether oil in water or water in oil emulsion will result. Oil in water emulsifier are formed when HLB of emulsifier is within the range of 9 to 12, and water in oil emulsion is formed when the range is about 3 to 6. So, it would appear therefore, that the type of emulsion is a function of relative solubility of surfactant, the phase in which it is more soluble being the continuous phase, and this is what we get this is what the rule of Bancroft says. Okay. Next mechanism is multimolecular film. Multimolecular film means hydrophilic colloids generally act by forming multimolecular layer at the interface. They can be regarded as surface active agent because they appear at the oil and water interface. So, another theory of emulsifying agent or the mechanism of emulsifying agent is multimolecular film. So, this multimolecular film is in this generally we consider the hydrophilic colloids, okay, such as acacia, gelatin, and they what they do, they act by forming a multimolecular layer. So, in the monomolecular film, there if we take the blend of or a combination of surfactant, they form a single layer, they form a mono layer at the interface of the oil and water. But here they form a multimolecular, multiple layers at the interface, and they can be regarded as an surface active agent because they align themselves at the oil water interface. They differ, however, they all differ from the synthetic surface active agent in that they do not cause an appreciable lowering of interfacial tension. They form a multi rather than monomolecular film at the interface. Okay. So, multimolecular films, they generally do not appreciably reduce the surface tension, okay, or they do not they do not appreciably reduce the interfacial tension at the interface of the oil and water, but they form a multiple layer of film at the interface, okay. Thereby they prevent the collision between the two oil globule. So, if we see in this figure that this is a oil and water type of emulsion, we had a take a hydrocolloids, that is acacia or a gelatin. So, at the interface what they happen, they form a multiple layer to prevent the collision between the globules of the dispersed phase. So, their action as emulsifying agent is due to mainly to the latter effect, because the film thus formed are strong and resist collision. So, their tendency or their nature of emulsifying agent is the function of the emulsifying agent is mainly due to this reason, that they form a multiple layer at the interface rather than reducing the interfacial tension. Actually, they form a strong condensed film at the interface, which resists the collision between the two globules of the dispersed phase. An auxiliary effect promoting stability is the significant increase in the viscosity of the dispersion medium. So, another effect they also impart, since they are hydrocolloids in nature, they are soluble in water and they have the property to get swell in contact with the water. So, they little bit increase the viscosity of the dispersion medium. Because the emulsifying agent that form multi-layer film around the droplets are invariably hydrophilic, they tend to promote the formation of oil in water emulsion. So, generally they are these emulsifying agent, they produces a multi-layer films around the droplets of the dispersed phase, and this layer is hydrophilic in nature. So, they have the tendency to form a oil in water type of emulsion, since hydrochloride they promote only oil in water type of emulsion. Okay. So, another theory is solid particle adsorption film. In this we take a finely divided solid particles that are wetted to some degree by both oil and water and act as emulsifying agent. Okay. So, in this we take a finely divided solid particles, solid particles or a finely divided powder particles, and the nature or the quality of such type of solid particles are that they have the affinity for both oil and water, that is why they act as an emulsifying agent. So, finely divided solid particle adsorb at the oil water interface and form a rigid film of closely packed solid. This film acts as a mechanical barrier and prevents the collision of the globules. So, these tend to produce a coarse emulsion. So, if we see that for the solid particle we take a bentonite or a V-gum. So, they form a, what will happen, they form a very closely packed solid film. Okay. This is the, since this is they are finely divided solid. So, they form a very close solid film around the globules of the dispersed phase and thereby prevent collisions. Okay. Then depending on the affinity of the emulsifier to a particular phase, one can prepare both type of emulsion. So, depending upon the nature of the emulsifying agent, and we can prepare either powder water in oil or oil in water type of emulsion. So, powders that are wetted preferably by water form oil in water emulsion, whereas those are easily wetted by oil form a water in oil emulsion. So, powder which preferentially get wet by the water, they form oil in water emulsion, and the powders which get wet by the oil, they form water in oil emulsion. For example, bentonite, graphites, magnesium hydroxide. Okay. Thank you.